Yeah, cars are a really great example because we of course ride in a car every day, and so you want to make sure that your car is safe, also to keep your kids safe too. And so whatever you can do to increase this time, that's going to cut down on the force. Okay, and we describe this as something called J, or our impulse. Right? And impulse occurs if your momentum changes, right? So you can think of impulse as a change in momentum. So if I have a bouncy ball here, okay, then my bouncy ball, when it bounces, its momentum is almost the same before and after the collision. It doesn't quite go as high. Why doesn't it go all the way back up? Why does it get a little bit lower? Yeah, it's not perfectly elastic. Where's some of that extra energy go? You can hear it, that's true. Yeah, so some of that energy goes into sound. Where else does some of that energy go to? Maybe heat, right? When you compress things, some of that energy goes into heating up the atoms. They start to vibrate, or you compress it a little bit, and so, but you lose energy. Maybe it crumples a little bit, or the ball starts to break. Okay, and I've got my sensor here. I'm not going to actually drop my sensor. But now let's look at something else here. Okay, if I drop my box and the ball, which one had a bigger change in momentum? Yeah, the ball did. Okay, so that means that my impulse was higher for my bouncy ball, right? So and let's talk about impulse, okay? So that's force times time. So for my bouncy ball, okay, maybe it was something like this, right? So if my let's say my velocity before the collision, right? So delta P for my bouncy ball, let's say it weighs 1 gram. So I'll have 1 gram. Well, we'll do my P final minus P initial. Okay. So then this would be M times V F minus M times VI. Okay. So then if this was say 1 gram, it would be 0.01 times, and we'll say it got to 1 meter per second. Okay, then this would be, if I say that this was downward, actually my final velocity was up, right? So to make sure my friends online can see since we're writing on the board. Okay. All right. So then here's my ball. It's headed downwards. This will be 1 meter per second. 1 meter per second before the collision, and this would be minus because it's headed downwards. And then when it's going up, right, the bouncy ball will be about 1 meter per second, right? So, and let's see, instead of a bouncy ball, I'm going to use maybe some paper. Let's see how many. Okay. This weighs about, I guess I lost my bouncy ball. Oh well. Oh, there it is. Okay. So these are about the same. And if I drop one, okay, this one didn't bounce. So it just kind of sits there. So its collision time is much longer. So for this one, then my total change in momentum will be 0.001 times this. So it'll be, I'll have 0.001 times my final velocity, which will be 1 meter per second, minus my initial velocity, which is 1 meter per second. Okay. So then my total change in momentum will be 0.001 times 2 meters per second. Oh, and then I've got a kilogram from that because of my bouncy ball is 1 gram or 0.11 gram. Then my change in momentum, it will be 0.002 kilograms meters per second. Okay. Now, for the other one, since it didn't really have a velocity afterwards, right? So then its final velocity, let's say is 0. Okay. Then so for the paper ball, this is for my bouncy ball. Then for the paper ball, I'll say if my mass is the same, 0.001 grams, my initial velocity, let's say, is also 1 meter per second, but my final velocity is going to be 0. Actually, this will be, my final will be 0 minus a minus 1 meter per second. So then my impulse is just going to be 0.001 kilograms times meters per second. That should be kilograms. Okay. So the paper ball, it has an impulse of 0.001 kilograms meter per second, and the bouncy ball has an impulse of 0.002 kilograms meters per second. Okay, so that means that if the area under this curve, okay, is the same, well, let's say it's for this one. This is my bouncy ball. Okay, that's for my bouncy ball. And my paper, well, the collision looked like it took longer. So here's my paper ball, okay? Whereas this one, it shoots back, okay? So let's say if this is my bouncy ball, then here is my paper, okay? So this is my paper ball, okay? Then the area under here is going to be less than the area under here, and my average force will also be smaller. Okay? So the area under here is smaller, and hopefully my average force is smaller too. How do I find the average force? I basically start right here and I make a line across there. And so I say, all right, about halfway, that's my average force. So for my paper then, if I did up here, okay, then my average force is smaller than this one. So if I can increase the time of my collision, then I can lower my average force. Okay? And this is something that they do in cars also. So when you have a piece of paper and it hits it, okay, probably the paper deforms a little bit. And this is something that's really important for automobiles because in the automobile, they add something called crumple zones. Have you guys heard of that? What does a crumple zone do in your car? Yeah, and how does that help you during a collision? Yeah, it's like bending your knees. It makes a collision take a little bit longer. You don't bounce as much. And also, we haven't talked about energy yet, but if your crumple zone takes a certain amount of energy in order to deform it, then some of your kinetic energy will go into deforming that material. And so you can take, if let's say you're going at 60 miles an hour, then some of your kinetic energy and hence your velocity will be taken by that crumple zone. So it's like you slam on the brakes, right? So a lot of times when you're about to get into an accident, you obviously want to hit the brakes because you'll have less kinetic energy when you crash. Now you can also do that with crumple zones because that will take some of the energy from you during the crash, and so it'll decrease your velocity, but it also increases the time of your collision. In fact, anything that you can do to increase this time is going to help you during a collision. Now, with football players in the NFL, this is a big problem because when football players take a really big hit to their head, the issue is that you don't want the average force to get too big, because if your average force gets too big, that's going to cause a concussion. All right, and so this is something that has been changing over time. And like in the 20s, as I said before, they had just a thin leather helmet. Okay, that could maybe help you a little bit, but not a lot. And so a lot of brain injuries come because, and also your brain is sort of floating around in this fluid in your head. It's not super well attached. And so sometimes if your head suddenly stops, your brain can continue on inside of your head. And if it hits the front of your skull, that can cause a traumatic brain injury. So you can get a bruise in your brain. And so this is why wearing a helmet obviously is much better, especially with a bike. So if you ride a bike, you should definitely wear a helmet. When I was a kid, they were just trying to get people to wear helmets, and they're like, it can save your life. And everybody's like, oh, helmets are stupid. You look so lame. But it really is a good thing because let's just say that if you're wearing a helmet, that can dramatically decrease the time if your head hits the concrete. It's going to spread out the force, first of all, but it's also going to increase the time of the collision. Whereas if your head just hits the concrete, that's really bad because your head will bounce, and the average force during the collision is going to be much higher. So here's my idea for football players. What they need to do is make the helmets bigger and actually make crumple zones in their helmets, okay? So you could have like aluminum cells or something like that. So when the football players hit each other in the head, you've got these crumple zones where the helmet will actually deform a little bit, and then you can lower this average force. So what I'm talking about is making their helmets like this big out of, I don't know, some kind of crushable foam or maybe aluminum cells, okay? And every time they would get in an accident, then of course they would need a new helmet, which, you know, so I guess maybe this would be a good business for you guys to start, because you could get the NFL, and every time a player gets tackled, then they would need a new helmet, and each helmet would be like $1,000 or something. So I don't know. That sounds like a good business opportunity, and you could save lives. Okay, so yeah. So hopefully, you know, when they go for tackle, they're not hitting the other person with their head, but you can't always control that. And so, but this is the idea. So you want to increase delta T. Okay. Another example would be, let's say, well, yeah. So if I increase delta T, then I'm going to decrease the average amount of force. Now, let me get up on the table again. Okay. I'm going to move this out of the light. Now, if I fall forward and I catch myself with my arms, it's going to hurt a lot less than if I just smack my face, right? So I'm going to try and, So I made it take a lot longer, and your body kind of adjusts for this, right? Because it's your natural reflex. You want to try and stop yourself. Now, if you've ever, have any of you guys ever been snowboarding? Have you fallen really hard? Are you supposed to catch yourself with your hands when you fall? Maybe.
I do.
Well, I always did too, because I love snowboarding. And I tried to teach my wife how to snowboard one time. And so everything was going great until the end of the day, and she started getting really tired, and she fell. And she tried to catch herself with her arms, but the problem is that her arm hit her rib. And so she caught her arm, and she didn't get a traumatic brain injury, so that's good. But so your body kind of will, your reflexes will, it's better, it thinks, I guess, for you to break your arm maybe or your rib than to hit your head on the ground full force. So your body kind of adjusts for that, but you might break your arm. So hopefully you break your arm rather than getting a traumatic brain injury. All right, so let's play a game. Nick, why don't you and I be partners and you guys be partners? So let's all come down here. We're gonna play a game. Okay, so maybe you guys have played this. Okay, so I want you to stand right next to each other. Okay, you're not allowed to move your feet. Okay, so you have to stand like this. Get kind of close, and you have to try and get the other person to take a step forward or back, just anywhere. Like if I hit your hands and you step back, then I get a point. Have you played this before? You never played this before? Oh my god! Have you guys played this before?
No. Can you Zoom friends see it?
Oh no! Okay, let's do it. Let's do it on Zoom.
I think see it.
Oh yeah. Okay, so let's go over here. Okay, so I guess this is called the. Yeah, come over here, guys. You guys play too. Okay, let's.
You just straight up like shove the person?
Well, yeah. Now see, this is a game about Newton's law. Okay, so here, come over here. You guys come over here so they can see you. No, wait, we're going the wrong way. All right. So if you've never played this before, okay, so you have to try and get the person to take a step. You can only hit each other's hands, and if you step, then I get a point. And if I step, you get a point. Okay, so come on, you guys have to play too. Come on. Oh. Oh. See, oh! Okay. Okay, we have to get whoever gets to 3 points, then we can stop.
Is the point to like absorb the push?
I don't. Oh, okay. Okay. So this illustrates if you push on someone, they push back, right? And so this kind of is like impulse a little bit. And it's a fun game, so you should play with other people. You guys never played that, really? When you're It is a fun game. Okay. All right, so there was a good video. Oh wait, it's not on the screen. Okay. Did I hook it up? Okay. All right, so this is a summary kind of what we've talked about. Okay, so we know that force is equal to mass times acceleration. Okay, so if we take our acceleration and we divide it both sides by mass, we get F over m equals a average, but our average acceleration also equals the change in velocity. Okay, now this does come from calculus, but that doesn't really matter because all that we need to know is we're just finding the area under the curve. Okay, but let's watch this video.
Dr. Wisby,
Yes.
you're not sharing your screen.
Oh, okay. Okay, there's only one slide. Here we go. All right, can you guys see the slide now?
Yeah.
All right. All right, so let's watch this. Let's watch this video.
Now, I'm gonna have another puzzle for you folks to consider, and this involves the happy ball and the sad ball. Okay, so we have the happy ball, just bouncy, bouncy. And then we have the sad ball. Although
Can you guys hear it online too?
Yes, we can.
a program at a school where there was
Wait,
a
but you guys
kid who
can't see it, right?
objected to my characterization. He said, no, this is the happy ball.
Now you can see it, right? Oh.
Because it's just hanging out. It's just chilling. It's relaxing. This one is like the unsettled ball. It can't decide what it wants. It can't. And so we can have the unsettled ball and the happy ball, okay? So we're going to take these. I'm going to roll them down a ramp. I'm going to put a ball here. I'm going to roll it down the ramp, and it's going to hit the block. And when it's going to hit the block, there's going to be a collision, and collisions entail forces. Here's the happy ball, the one that doesn't bounce. And here's the unsettled ball, the one that bounces and can't decide what it wants. Ooh, the one that bounces knocks the block over, and the one that doesn't bounce doesn't knock the block over. And that's a bit of a puzzle. That's a bit of a puzzle that we're going to return to. That will knock the bouncing, good. Not bouncing, not enough. So it turns out, if you have a collision with something bouncy and a collision with something not bouncy, which one exerts more force? The bouncy one. Why does landing with a bounce cause more force than landing with a thud? That's something that we're going to consider. That's sort of a puzzle. Ask this question. Do you want a rebound or not if you're going to minimize the force and the impact? And we already saw this. We already saw this with these two balls. If you want to minimize the force in the collision, you don't want to bounce. You don't want to bounce.
I really like that experiment. I don't know what that ball is that didn't bounce, but I want to make one of those. But I couldn't do it quick enough for class, so otherwise I would have just done it. But that's really cool because it shows you that if there is a rebound, the force is actually higher, and he could knock over that block. So because the bouncy ball rebounds, then its impulse is bigger, and so that means that the average force is higher. The one that doesn't rebound, it has a lower impulse, and so the average force is smaller. Now, do you guys know who Bruce Lee is? Do you know who Bruce Lee is? Yeah? Okay. So Bruce Lee was an amazing martial artist, and one of the things that he taught was that if you punch someone, you can exert more force by pulling your hand back. And so what he would always try and do, and I don't know if this is true or not, but we're going to test it today. I'm not actually going to punch anything. But he said that when you punch, if you pull your hand back quickly, the force will be higher, because he could do these, maybe this is video, he would always do the 1-inch punch, and he could supposedly knock people over. Of course, there's cinematography, and so who knows what was real or not. And now, a lot of Bruce Lee, it's kind of legend by this point. So, but this is something that I have always wanted to test, and now I have a physics sensor so that we can actually do it. So we're going to actually test this during me punching, and we're going to see which one produces the highest force. Okay, so let me plug this in. And so now we're going to test if this legend is true from Bruce Lee or not. Okay, so I'm going to turn this on, and I'm going to use the accelerometer. Okay, and if I use the accelerometer, then let me share my screen. All right, so there's my accelerometer. Start recording. Okay, and I am going to go like this, and then I'm gonna go stop there, and then let's see which one had the bigger force. Oh, stop. All right. Okay, so the first one here, I guess this is one where I didn't. And I was holding it like this. So I guess let's look at AX, not C so much. Okay, that one looks pretty high. Okay. Oh, it looks like I I maxed out the sensor. Okay, well, let's do it a little bit more and let's try again. Because I think that the acceleration, it's kind of, all right, let's try it. I'll do it in slow motion. Okay. So I'll take it like this and I'll just go, ooh. And then I'll do it again and I'll say, oh. Okay. So we're testing Bruce Lee's 1-inch punch. Okay. So let's look at our data. All right. We've got our first one. Let's zoom in. And we'll just do a AX. That's the direction that I was punching in. Okay, so this one got up to 35 meters per second squared. Okay, and then let's go over to the other one. Well, one thing that we can say from this is clearly I'm not Bruce Lee. Now the other one, well, let's see. So it looks like, I don't know. What do you guys think? Now, it does look like maybe the one where I pulled it back is slightly higher. It's hard to say though because our force sensor is not able to pick it up as much. So, I guess it's inconclusive. But it does look like the one where I pulled it back is slightly higher, although it's hard to say. Okay, well, let's take a break, and then let's be back in about 10 minutes. All right, this will be my last attempt to understand the 1-inch punch. Were you reading about it? What did you find when you read online?
What I could find, I don't think it works.
You don't think so?
It looks like the amount of time that it takes the punch to get to the person is what is determining its overall force. This time matters, but pulling it back doesn't.
It doesn't matter.
That's what they said.
Oh, so basically, if you can punch them faster, then you do more damage.
Yeah.
Oh, okay. So, and why would that makes sense? Why would punching them faster do more damage?
Well, I'm assuming there's less time, so that the force increases.
Well, if you can move your arm faster, then your arm's gonna have more kinetic energy, right? So, and that's the thing that maybe when you're punching is important. So the amount of kinetic energy you have is what's gonna do damage. So when you hit them, you'll have more force basically, because you'll be going from a higher velocity. And I guess when your fist stops, then there'll be a bigger change in velocity, and so a bigger acceleration. But they said pulling it back doesn't matter. Okay. So then what you're saying is the legends that I heard about Bruce Lee are a lie. This is a sad day, guys. But that's okay, because this is physics, and so we can check it. So maybe my childhood hero Bruce Lee, maybe it was a myth, but it's an interesting story. So let's check it and see. All right. All right. So here I do. So I built a track for my little cart. I've got my force sensor here. Now it's only okay, maybe it needs to be a little higher, but it's not very high, and so we need a little. Okay, there we go. So because the force is limited that the sensor we can measure. Okay, so let's do one where I've got some twine here. Let's do one where I pull it back, and then let's just do another one where it hits, and then we can see which one gives us a higher force. And then this will allow us to test Bruce Lee's 1-inch punch. And I'm a little sad that maybe what I understood as a teenager was a lie, but that's okay. He doesn't like what? Okay. Well, I have no idea. All right. So we're gonna do our initial run. I guess this napkin holder. Okay. All right. So we'll do the initial one, and I'll start it. I'll just lift it up so it goes down the thing, and we'll see. Okay, so I'm going to use the force sensor this time. Okay, so this is. Oh. There we go. Okay, so this is without me pulling it back. Okay, so we got a force. Oh, that was the wrong button. And now, let's do it with me yanking it back and see if there's any difference. Okay, I'm gonna start here. Okay, maybe that was too hard. Did it even record it? Is it? Yeah, that's what I was thinking too. That's that's how Bruce Lee would have done it. Yeah. Okay, let's. Oh well, I did. Okay, I think I'm maybe I messed up the sensor. Let's look here and see. All right, so I got up to on this one. I got to 4.5 newtons, and then on this one, oh, it was a little bit higher. Maybe let's try it. Let's try it again because I maybe was a little too eager to. Oh, now I probably broke it. Oh no, there it goes. Okay, we'll try it one more time. But it looks like on this one I may have gotten an extra 0.5 newtons. So, all right, let's try it one more time. Okay, so we're recording. And I'm gonna put it here. Recording. Recording. Maybe. Well, I guess we can do one more where I think that got it. This was 4.5 and this one was, well, it's hard to say. I can't tell. So I guess it doesn't seem like that there's a lot more force there. But well, hopefully you don't ever have to punch it. I guess we can't really say because we would need a force sensor to actually measure somebody's punch. And since we don't have that, we can't really say for sure. But I think what you said maybe makes more sense. If you can get your fist to somebody faster, then that means you'd have more kinetic energy, and so that would hurt more. So Hopefully you don't ever have to actually punch anyone. But if you ever had to defend yourself, then hopefully you would. Okay, so let's that could be too, but or maybe Bruce Lee was just an amazing martial artist, and we'll never know. And it was also a lot of really good movies. Okay, so let's look at this example. Okay, we've got um, two ice skaters here. Two ice skaters, Sandra and David, stand facing each other on a frictionless ice. Sandra has a mass of 45 kilograms, and David has a mass of 80 kilograms. They then push off from each other, and after the push, Sandra moves at a speed of 2.2 meters per second. Right? So this is an important problem about conservation of momentum, because if these two people push off, that means that momentum has to be conserved. So their momentum has to be equal and opposite to each other. Right? So if we know what Sandra's momentum was, we know her mass, and we know her velocity, then we can also figure out what David's velocity has to be too. Now, what's the total momentum of the system going to be after the collision? Because it was 0 before. So after this, I guess this is kind of like an explosion. So if it was 0 before the explosion, where they push off from each other, then what does it have to be afterwards? Yeah, it also has to be 0. So we can say their momentum before they push off and after they push off has to be 0. So then if that's true, then we can just set up an equation, and that's when they say strategize. So think about the problem and say, all right, at least what I would do is say my momentum is the same before and after, and so I can set up an equation now, and I can say, all right, I've got the skater's final momentum has to equal their initial momentum. So momentum before has to equal the same as momentum after. And this is the same way that rockets work, right? So when a rocket is traveling, the thing that makes it accelerate faster is it basically throws a bunch of mass this way. And if it throws mass that way, then it pushes the rocket the other way. Jellyfish do the same thing. They basically suck in a bunch of water, and then they push it out behind them, and then they can swim. So the momentum of the system doesn't change. The momentum is still conserved. If you think about the system as both in this problem, David and Sandra. So our system is the two skaters, and the momentum of the total system hasn't changed. All right, so we say, all right, momentum before equals momentum after, and our initial momentum is 0, so then our final momentum has to also equal 0. Sometimes it's not 0 initially, and then it's a little bit more complicated, but in either way, we can use some algebra and figure out the right answer. So maybe let me write it out. All right, so we have our initial momentum equals our final momentum. So mass of Sandra times Sandra's final velocity plus the mass of David plus David's final velocity. Okay. And our initial momentum is equal to 0. So this all equals 0. And I probably didn't pick the best labels, but I can keep track of it in my own head. Okay, so Sandra's mass was 45 kilograms, right? And so we just add it together. So we'll put this in here. And now this all equals 0. And so I can plug in my numbers now. Actually, first I'm going to move this to the other side. And I'm going to say, one of them has a negative velocity because they're going in opposite directions. And so I'm going to say, let's say Sandra is negative. Okay. So we'll say, all right, her velocity is going to be negative. So it'll be, actually, I'm going to move everything to the other side first. So I'll subtract MSB final S from both sides. So this goes away, and now I have one on the other side. Okay, then I have Sandra's final momentum equals the negative of David's final momentum. Now I'll put in my numbers, and I'll say her velocity is negative, so this will be 45 kilograms. This is negative times a negative 2.2 meters per second is equal to his mass, which is 80 kilograms, times his final velocity, which is what we're after. So then I'll just divide both sides by 80. And now I can plug that into Mathematica. I'll say my negative signs go away. So 45 times 2.2 divided by 80. So that's going to give me his velocity should be 1.2 meters per second. So I'll get 1.2 meters per second for David's final velocity. And in the problem, they had them going in the opposite direction. Mine was I switched the negative sign, so I came out with a positive, but his is if I would have said his velocity was negative and hers was positive, then my negative sign would have been different and it would have matched the problem. But I said she has a negative velocity. Okay. All right. So we can have lots of particles together. So we can have a system of thousands or even hundreds of particles if we wanted to, although it gets really complicated then. Usually we just keep it to 2 or 3, but we could do more. And you just add up all their initial velocities in the x direction and that has to equal their momentum, their final momentum in the x direction. So we can have we have conservation momentum in all directions. So you could have something in x and y. You guys ever play pool? So that's a great example of two-dimensional conservation of momentum, because then you have to think about, all right, where is my pool ball is going to come in? It's going to go off at some angle, and so then my momentum is still conserved, but it's a little bit more complicated in pool because you can also add rotation to the pool balls, and so it's not so easy as you can transfer angular momentum. It gets really complicated. I've always found that when you play pool, it's almost impossible just to have simple conservation of momentum, because if you put any spin on the cue ball at all, it affects where the ball is going to go. So if your cue ball comes in like this and it's rotating, it's going to transfer some of that rotation to the ball that you hit. And so you also, besides just having conservation of momentum, you also have conservation of angular momentum. And that somehow affects how the pool balls go. That's a little bit more complicated. Usually they don't talk about that in physics textbooks. It's okay. But we could do this with a system of many, many equations, okay? And that's fine. So we can solve these equations. Sometimes we have to solve a system of equations if there's two dimensions, but that's okay. Let's look at another example where we have a boy running, or a girl, and this person runs and jumps on a sled, okay? And so now we have to think about what's the new momentum of our system. So when he jumps on the sled, if the sled weighs 5.9 kilograms, okay, then is the velocity of the system going to be slower or faster after he jumps on it? Yeah. Well, let's see, he's only got 4 meters per second, okay? So will the velocity of the sled be greater than or less than 4? Why don't you guys talk about it? There's only 3 of you, so you can just talk to each other. Well, let's try it here. I've got this chair. And I'm going to make it so okay. Okay, here's my chair. Let's see if when I jump on the chair, if it's going slower or faster. I think it was, what do you think? Was it slower or faster? Let's try it again. This time I think the chair has a lot of friction. So I think it's going slower because the momentum of the system has to be the same. And so if we add a bunch of mass, then that's going to, I think it's going to slow it down. So our final velocity will end up being slower, but we can calculate it. Oh no, I guess they don't calculate it. Well, let's calculate it on the board, or actually on my paper. Okay, so the sled's velocity so here's my sled. My sled's mass is 5.9 kilograms, and the person had the mass of the boy is 26 kilograms. And his velocity is 4 meters per second. Okay. So then the question is, all right, so here's our human. So he jumps on the sled. And then what is the final velocity of our system? So very important if you are a bobsledder, right? But actually they hold on to the sled and they get their momentum build up before they jump on the sled, okay? So they try and get the sled going as fast as they can so that when they jump on, then the velocity doesn't increase at all or decrease at all. All right, so our initial momentum, so the initial momentum, we have MVI of the sled plus M initial of the boy, and his initial velocity is equal to our final mass of the sled times our final sled velocity. And but now actually we just have we only have one object at the end, and so because this is what's called an inelastic collision. So an inelastic collision is where the things stick together. So if they stick together and they don't bounce off of each other, that's inelastic. The bouncy ball, that's an elastic collision. Okay, so now we just add, we'll have they're going at the same velocity, so we can write M of the mass of the sled, and our sled doesn't, the masses don't change, and the mass of the boy, they are connected, and their final velocity is different than the first one. So it's supposed to be our final velocity of the boy and the sled. Okay, so initially the sled has 0 velocity, so that term just goes away. And so now we have this, we have that our initial mass of the boy times his velocity equals this, and we have the two masses together. So we'll say the mass of the boy is, actually we can solve for this first. So we'll say MIB times VIB divided by mass of the sled plus mass of the boy, all equals our final velocity. All right. So if I plug that into Mathematica, then I will have 2. Oh no, wait. His mass of the boy was 26 times his initial velocity, which was 4 meters per second. And then all of that will be divided by the mass of the boy plus the mass of the sled, which is 5.9 kilograms. Okay. So that tells us that the final velocity of the sled then is going to be 3.2 meters per second. So when he jumps on the sled, he's now more massive, and because he's more massive, the velocity is going to be slower. So a better way to do it would be if he were to hold on to the sled and start running and then get up to 4 meters per second. And then once he's holding it and you're already attached, then you can jump on it and you'll go much faster. Okay. So this is also important if you have a skateboard and you try and run and jump on it. What will happen is there'll be a sudden change in your velocity, and usually your center of mass will continue to go forward while your legs are actually going slower. And so usually you fall and it hurts a lot. So all right, let's see what else to talk about. Momentum. Oh yes, let's talk about rocketry. All right. An explosion is when the particles of the system move apart after a brief, intense interaction. So this happens during when a rocket is taking off. Okay. So here we've got the momentum of the rockets, and we also have the momentum of the ejected material. So this is our gas coming out of it, right? So this is how all rockets work. And you start off and the momentum of the rocket is 0. It's on the launch pad, it's stationary. And then you have this chemical reaction, and the chemical reaction shoots mass out of the back of the spaceship. And as you eject this mass, they're going in equal and opposite directions. Well, no, they're going in opposite directions at very different velocities. But then the momentum of the rocket changes a little bit, right? Now, rockets are typically huge. They're really massive. They're the size of a building. And the ejected material is much less massive, but it's going at a very high velocity. And so by doing that, then you can blast off and go into space. Now, the problem with this kind of rocket is that if you want to go anywhere, you need an incredible amount of rocket fuel, and it's really expensive. If you go to the Science Center, there's a scale you can stand on, and it tells you how much money and rocket fuel it would take to launch you into space. And I think for 1 carton of milk, it's about $100,000. It's really, really expensive. It takes a lot of rocket fuel to get into space, and it makes a lot of pollution, and it's very inefficient. And so people are trying to work on alternative means of propulsion in space. We don't really have any right now, but if we want to really go anywhere in space, we've got to move away from conventional rockets. Probably at some point we're going to run out of resources on Earth. If you look at our society, and this really came into light as I was moving, I realized what an incredible amount of trash that humans make. We really just make a lot of trash. My apartment was full of trash. I mean, it wasn't full of trash. I mean, just normal things, but we really make a lot of trash. And so if we continue consuming resources, we're probably going to run out on the Earth eventually. I mean, maybe in 100 years, 200 years, or 1,000 years. I had a friend in geology that said there is a finite amount of oil. Now, at some point, we're going to reach a point where it's going to be so expensive to get more petroleum fuels that it's not going to be worth it anymore. So for example, you could pay $10 a gallon for gasoline. Would you be concerned about that? Now, they already pay $10 a gallon in Germany. So if you go to the gas tank and you bring your SUV to the pump, it's going to be a few $100s to fill up your tank, which is why in Europe, people drive much smaller cars, right? Because it takes much less energy. But we here in America, we like big cars and we use a lot of gas. The price of gas is the same here as it is in Germany. They just charge more taxes. So, but people drive smaller cars that are more fuel efficient. You know, just two different ways. But either way, if we keep going, we may have to go to another planet at some point. And if we need to do that, if that planet is on another star, we're going to need to find a different means of propulsion. So maybe something like Star Trek. I don't know about actually Star Trek, but something different than just rockets, because rockets are not going to do it. We gotta find something else. So we could maybe get to Mars, but going beyond Mars is going to be tricky. Okay, so this is how a rocket works. Basically, if you're on a rocket, if I have to do it. All right, so if I'm on this part, and I am standing here, and I jump off, then I moved a little bit this way, and it pushed me back that way. So if I try and really push off the cart here, this is my rocket. So if I stand on my cart, I really try and well, I think it's okay. I did move a little bit that way, but I'm a lot more massive than the cart, so I had to give it a push really hard that way. So all right, so we use chemical fuel. Burning this organic matter expels it out of the back. The total momentum of the system is conserved, but the rocket will start taking off then. All right, so the two boxes on a frictionless surface, they have been sitting together at rest, but an explosion between them has just pushed them apart. How fast is the 2 kilogram box going after the explosion? Two? You guys all think it's 2? Okay. Yeah, because if we were in medical school, I would just call on people. But I'm not going to do that. Not in medical school. Yeah, so it's if the smaller block is going to the left and it's 1 kilogram and it has a velocity of 4 meters per second, then its momentum is 1 times 4. And so then we need to get 4 on the other side. So we'd have to say, all right, we got 2 kilograms, multiply that by 2 meters per second. So then its velocity has to be 2 meters per second going the other way. All right. So example, speed of a toy rifle. A 30 gram ball is fired from a 1.2 kilogram spring-loaded toy rifle, the speed of 15 meters per second. What is the recoil speed of the rifle? Now, if you've ever fired a gun before, hopefully you know that you want to hold the gun against your shoulder, because that way it's attached to your shoulder. Because if you don't, if you have the shotgun out here and you pull the trigger, the gun will have momentum and it will travel back, and it could break your arm. So if you fire a gun, that recoil could come back and hit you in the arm. So you have to keep the gun securely against your shoulder, and that's very real. Okay, so our pellet is traveling at 15 meters per second, and what was its mass? The mass was 30 grams. Okay, so again, in this problem, we want to say our initial momentum is going to be 0. And so then our final momentum has to also be 0. So then we just do this just like we did the ice skaters. We say, all right, the momentum of our pellet has to equal the momentum of our rifle. And we know the mass of both of those objects. We know the velocity of one. So now we can find the velocity of the other. So their final momentum is different, but their initial momentum is 0. And those two things are both in our system that we're considering. Okay, so let's talk about inelastic collisions. So this is when two things stick together. They collide and they stick together. Okay, so this is similar to what we had before. Right now, the blocks are sliding towards each other. So one block has a momentum of 4 meters per second to the left, and it weighs 1 kilogram. The other one is 2 kilograms going the other way. Then they collide. So what is their final velocity going to be? Which direction will they be moving? I would take a boat, but there's so I heard two people say 0, right? Because they have equal and opposite momentum. So when they collide, they have to stop with each other. Okay. And this is also something to think about next time you're texting on your cell phone. If you're driving a car and you're in a little Prius like me, and you were to collide with a semi truck, which can happen if you're texting, don't text and drive. If you hit that, your little tiny Prius, actually Priuses are kind of a little massive because of the battery, but if you hit something much more massive, then the semi truck might not even feel your presence. For example, like a train. A train is huge. It has a really large mass, and if you get hit by a train in your car, the train might not even stop. It might slow down a little bit. But if you collide with that train, it's not going to really affect it that much. So in a collision, the little car is probably going to lose if you're both traveling at the same speed. Okay, so here's our two train cars. Assembling a train from several railroad cars, two of the cars with masses of 2 times 10 to the 4 kilograms and 4 times 10 to the kilograms are rolled towards each other. When they meet, they couple and stick together. The lighter car has an initial speed of 1.5 meters per second. The collision causes it to reverse direction at 0.25 meters per second. What is the initial speed of the heavier car? Okay, so now we have, in our final system, they're stuck together. So the final part would just be the two masses, and we know their velocity after. We know the lighter car's initial velocity, but we don't know the heavier car's initial velocity. Okay, so we can set up our equation, and we'll say for these two, we're just going to consider the mass, the momentum of one particle, and that has to equal our initial momentum. Okay, and so now we get this equation here. So we have our final momentum which is the sum of the masses of the two cars plus their final velocity. And then the only thing that we don't know is the velocity of the heavier one. Okay, so we can do some algebra, and now we can get that on one side, and then we can plug in our numbers, and we can get our final. So you're going to have to do some algebra, but this one isn't too bad. Okay, so let's go on a little bit. Now, if you have X and Y momentum, then you are going to have to use components for the velocity. Okay, so you'll have to figure out each pool ball's total velocity, and then you'll have to break it into X and Y components and solve those separately. And you'll have to remember that X momentum is conserved and Y momentum is conserved. So you can find its initial momentum and its final momentum. So in the case where the pool ball is flying up to hit the other balls, then you'd want to say, all right, X is in the direction of my initial object, so it doesn't have any Y momentum. Okay, that makes that can make your life a little bit easier, because then you say, okay, in Y, if let's say I had two pool balls, so over here, this one hits another ball, goes like this, then they both go off in different directions. And I'd say, well, initially, my initial Y velocity is 0. So that means momentum, and I'm going to say this way is X, and this way is Y. So initially, there's no Y momentum, there's only X momentum, right? So, all right, well, thank you for coming today, even though it was at the wrong time. I apologize for that. But tomorrow, we'll be back at the normal time, and I'll be here. Thanks for watching online, guys.
Hi, this is Jeff. I just have a quick question.
Yes.
For the test 3, so we will finish the test 3 during the weekend, and it will be covered the chapter 9 and chapter 5, right?
5, 9, and 10.
Okay, got it. 5, 9, 10. Okay, thank you, Professor. Thank you.
Okay.
Bye.
Bye.
Thank you. Like and subscribe down below.